Welcome to the recording of the common contaminants and the types of businesses that use them presentation from the Back to Basics Part 1, Developing the Conceptual Site Model and Site Characterization Plan workshop that NMOA hosted in March of 2018. The presenter is William Ottaway. He's the Chief of the Training and Technology in the Division of Environmental Remediation at the New York State Department of Environmental Conservation, where he oversees a team providing technical support for remediation of hazardous waste sites and interpretation of hazardous waste regulations. From 2001 to 2010, Mr. Ottaway was project manager with DEC, responsible for the cleanup of manufactured gas plant sites throughout New York State. He previously worked as a public health engineer and has also worked for engineering consulting firms. He has a Bachelor of Science degree in agricultural engineering from Cornell and a Master of Engineering degree as well. He is a professional engineer licensed by the state of New York. With that, I will turn the presentation over to Mr. Ottaway. Thanks, Bill.
Thanks, Jennifer. Okay, I'm basically going to run through some of the common chemicals that we're going to see at remediation sites. Definitely sort of a broad brush review of that topic. We'll start out looking at the inorganic chemicals, particularly metals. I wanted to start with those because we very often overlook them and focus just on the organic chemicals. Once we do get into the organic chemicals, we'll talk about just basically an overview of the chemistry, then start looking specifically at petroleum source as a source, coal tar, discuss chlorinated solvents and PCBs, and then a brief discussion about the emerging per and polyfluorinated alkane substances as an emerging contaminant. So first thing, what do we test for? There are thousands and thousands of chemicals out there, and how do we decide what to test for? And at least in New York, what we use is EPA's Target Analyte List, and that was developed for EPA's Contract Laboratory Program, or CLP. For the organic chemicals, they have a similar Target Compound List, or the TCL. In addition to the specific chemicals on the target compound list, they do also require TICs, tentatively identified compounds, to be reported under that program. And those tentatively identified compounds are defined in the CLP. Okay, New York State DEC recently began requiring analysis for the PFAS compounds, as I said, per and polyfluorinated alkane substances. This is the first time we've actually added chemicals to the TCL list. So this is a new thing for us. And who knows what the next thing we're going to be adding as we live in the new world of emerging contaminants. Okay, so the Target Analyte List has all the compounds that you see on the screen right now. And I've underlined the chemicals that are listed in RCRA as potentially hazardous waste materials. It's interesting to look at this list, particularly the ones that are not underlined, and you have a lot of substances in here that are really not toxic at all. Calcium, magnesium, these are things that you take supplements for. And the reason that these are properly analyzed when you're looking at a site is they're important for the soil geochemistry, and understanding how the chemicals will interact with the soil. A good example of this is the emerging contaminants, the PFAS compounds, and the solubility of those compounds appears to be highly dependent on which divalent cations are in that are present at what concentrations. So you're getting, yes, you are evaluating the toxic metals in this evaluation, but you're also picking up information about the soil, which will be important for the conceptual site model. There are a few different ways that you can test for these metals. Most of the health risk criteria are based on the total concentration of the metal in the soil. So if you're testing for lead, you might have a certain 10 parts per million or parts per billion of lead in the soil. If you're looking at characterizing the soil for waste disposal, and that would be relative to the record requirements, you'd need to test the TCLP, or toxicity characteristic leaching potential. Toxic characteristic leaching potential. Oh boy, missed that one up. But the TCLP, and that will tell you it's a very conservative test, a very aggressive leaching procedure that will tell you how much lead could, or how much of that particular metal could possibly come out of that sample. But that's not going to tell you what would come out of the soil under normal conditions. If you wanted to know that, what you do is the SPLP, or the synthetic precipitation leaching procedure. One additional note about the SPLP, I like this because it's sort of a good news thing. When the SPLP was developed a couple decades ago, there were two flavors of that, the East Coast and the West Coast. And the East Coast had a lower pH because of acid rain. And I talked to the folks in our Division of Air Resources, and at this time, the pH of rainwater has come up sufficiently in New York that it would be reasonable to use the West Coast protocol for the SPLP. Obviously, you don't need to use West Coast procedure, but if someone does come to you and suggest it, it's not a crazy idea. We actually have made some progress on the acid rain front. Okay, probably the most important of the metals that we're looking at is lead. The primary concern here is with direct exposure, either ingestion or inhalation, and no amount of lead is safe, especially for children. So this is a really important environmental toxin. It is considered a hazardous waste if the TCLP level is above 5 parts per million. There's one other consideration on the record side of things that I'd like to draw your attention to, which is that the LDR restriction, the land disposal restriction, is set at a limit of 0.75 parts per million, which sounds like it would mean you'd have to manage material between 0.75 and 5 in a different way. But there is an alternative standard for remediation waste, where as long as you have a 90%, you're required to have a 90% reduction in the TCLP with your treatment, capped at 7.5. So what that means is that for remediation waste, you do not have to worry about that 0.75 ppm limit. But you do need to be aware of it, but you should also be aware of the alternative standard that should eliminate the concerns there. Anytime you're handling lead remediation waste that does fail the TCLP for hazardous waste, be aware that chemical stabilization is available, which will decrease that TCLP and which would allow you to eliminate that hazardous characteristic. That's generally very much worth your time and money. It will bring down the overall cost of the remediation project if you can eliminate that hazardous characteristic and manage that as non-hazardous soil. So definitely be aware of chemical stabilization. It's been around for a very long time now and has been proven to be effective. Unless you have really low pH, lead has a relatively low solubility. So we're generally not looking at large groundwater, large plumes of contaminated groundwater when we're looking at lead-contaminated sites. You can have lead in the groundwater if you have high concentrations in the soil, but you can also get much higher levels in the soil if you have some acid conditions. One of our biggest sites is a battery recycler, and they do have some acid conditions that contributed to the groundwater conditions there. One of the interesting side notes, we do have contact with our Department of Health in New York City, and they regularly test consumer products to see if they have lead. And they found cosmetics with as much as 50% lead by weight. So remediation sites is not the only place where people will be exposed to lead. It certainly is still there in consumer products. The most frequent situation where you're going to come across lead is in historic fill. Back when we had leaded gasoline, there was air deposition of lead throughout the country and throughout the world. And there were other sources of lead that found their way into ash and landfills and so on, and that's where you get the lead in your historic fill. There are some mines in the Northeast. New York has a couple that we're currently remediating. Obviously, the mining industry is much bigger out west, and you're going to see much more mining and smelting out there. There was a report by USA Today some years ago, 5 or 10 years ago, mapping all the smelters throughout the country. And there are a lot of smelters in urban areas. So that is going to be something that people should be aware of. It's very, you will come across smelters as you're redeveloping your industrial areas, and you would likely find elevated levels of lead and other metals. We've certainly come across that in New York. As I mentioned, the biggest site that we've had in lead site that we've had in the state is a battery recycler. Lots of contamination from that manufacturing, that process. Another thing to be aware of is cathode ray tubes. They actually have several pounds of lead in each cathode ray tube. It's concentrated in the funnel, not the glass in the front of the screen, but the tube behind it is the highest concentration of lead. It used to be that the cathode ray tubes were recycled and they'd make new cathode ray tubes out of that leaded glass. At this point, everybody's using flat panels, so there's not a market for cathode ray tubes. As a result, we have a glut of waste CRTs, and throughout the country, we're seeing some illegal dumping, storage, inappropriate management of those. So there definitely is a potential for those post-consumer products to create sites in the future. Just for perspective, I wanted to introduce probably the largest lead site in the country. That would be out in Idaho, the Bunker Hill site. It was from a lead smelter, very large area, and a public health crisis to boot. That slide you see, chart you see in the lower left, shows blood lead levels in children. 50% of the children in this large geographic area had blood lead levels over 10 micrograms per deciliter. So we had half the kids suffering lead poisoning effects. This is spanning most of the Idaho panhandle from the Montana border all the way over to Coeur d'Alene. It was a large enough area that they were not able to go in and dig out all the contamination. Instead, what they did is they covered it and put in a use restriction. So anytime someone digs out there, they call dig safe, just like everywhere else, except anytime a hole is dug through the cover, the underlying soil is managed as a hazardous waste. They have their own hazardous waste landfill for that lead-contaminated soil, and this is one of the hallmarks of long-term stewardship being used effectively to manage remaining risks at a remediation site. Okay, next chemical that I want to talk about is arsenic. Arsenic is an acute poison. There's a famous play called Arsenic and Old Lace, made into a Cary Grant movie, where the characters were poisoning people. They had developed a tolerance, just like iocane powder. You can develop a tolerance for arsenic, so this is well known as arsenic was very well known as a assassination tool as well for poisoning people. Long term, it is a carcinogen, so it's not just the acute effects. The principal source that we see for in our area is from pesticide use, particularly lead arsenate, which was a very heavily used pesticide in orchards, particularly apple orchards here in New York, where that's such a major industry. And because it's, we see arsenic all over the place, every place you see an apple orchard, and because there's this perception of being able to develop a tolerance, it's possible for you to be a little bit lackadaisical about arsenic. But again, just to get a perspective, in Bangladesh, they had a huge problem with waterborne disease, and to eliminate that problem, they went through and replaced their surface water supplies with groundwater wells, and it did eliminate the problem of the waterborne disease. But as the water table was drawn down, the geochemistry of the aquifer changed, and the arsenic levels in those wells increased, and now 20 million people in Bangladesh are suffering from arsenic poisoning. And it's very severe, cancer, dermal effects, and arsenic can be a very, very serious contaminant. Next chemical I want to mention is chromium. There are two flavors of chromium, hexavalent and trivalent. The hexavalent is very toxic and very soluble. The trivalent is much less toxic, and it's almost insoluble. If you're aware of this, the pop culture reference for chromium is the Erin Brockovich movie, where hexavalent chromium was the chemical that was front and center in that court case and so on. One of the ways you can treat hexavalent chromium is by reducing it in situ, and that would convert it back to trivalent chromium, and you can eliminate the groundwater contamination that way. Unfortunately, you can move that process in the opposite direction as well. And if you're using in situ chemical oxidation in soil that has naturally occurring trivalent chromium, you can mobilize the chromium. I've seen results for an ISCO project where the initial results before chemical injection was the chromium level in the water was 15-20 parts per billion. Following injection of the oxidant, the chromium levels got up into the 2 parts per million range. So if you're doing a ISCO project and you have potential uses of that groundwater down gradient, definitely be aware of the potential for mobilizing chromium with that process. So as I mentioned, hexavalent chromium, the toxicity, it has very high toxicity. California went through the process of lowering their MCL in drinking water from 100 parts per billion down to 10 parts per billion. New York was similarly looking at lowering their MCL at the same time, but in 2017, the courts vacated California's lowered MCL because they did not adequately take into consideration the economic cost of that lower MCL. When you start looking at how much chromium would cost to treat, it would be very expensive. And to my knowledge, New York is not looking at lowering their MCL at this time. The final metal that I wanted to bring up is mercury. If you find elemental mercury at your site, it's very noticeable. It's bright silver, and it requires a specialized response, as you manage elemental mercury differently than we generally handle contaminated soil. It's more of an abatement process. So that certainly is one of those situations where if you find it in the field, that's the time to take a step back, call in the experts, and sort of start that part of the project from scratch. Deal with that as a separate activity. You do also find elevated levels of mercury in soil other than elemental mercury. It isn't all just bright silver beads, but that is something to be aware of. The disposal of mercury-contaminated material is even more difficult than normal RCRA requirements. There's two levels of land disposal restrictions for mercury-contaminated material: high merc and low merc. If it's high merc, you actually have to get it retorted, get the mercury out of that, and that mercury that's then extracted is actually stockpiled at a facility. It's not disposed of. They want to get this mercury out of the environment permanently and completely. Let's see, the other unique thing about mercury as metal is that it does create vapors. That's the principal exposure that we've seen. Industrially, mercury used to be used in the felting industry, and that's where the Mad Hatter meme came from. Probably the worst environmental exposure to mercury vapors was at a site down in New Jersey, where the Kitty College Daycare Center was housed in an old mercury thermometer factory, and the walls were filled with elemental mercury, and there were very serious health effects from the mercury vapors. So the elemental mercury is certainly something to be aware of and to take seriously. Just like lead in consumer products, mercury shows up in consumer products. I think the most disturbing element there is that there's a branch of medicine from India, Ayurvedic medicine, where they purposely add mercury to the supplements, up to 3% by weight. So that's a very highly toxic material that they're taking on purpose for medicinal reasons. Another thing that I'll just mention, metal plating sites can be interesting in all sorts of ways. Not only do they have lots of metals from cyanide to chromium, nickel, and so on, but they also have solvents that are used in etching the materials. There's acids that are used in cleaning materials, and even the PFAS compounds are used both for etching and for mist suppression in the plating processes. So metal plating sites can be, really interesting, really challenging, complicated sites to work on. Okay. Now, as I said, most of the time that we work in this industry, we're dealing with organic chemicals. the EPA's target analyte list has 4 different categories of organic chemicals. The volatile organic chemicals, those are the ones that will readily evaporate, ones that will cause the vapor intrusion that we all deal with. Semi-volatile organics don't volatilize as much. You might be able to smell them, but they're not going to be creating a vapor intrusion issue. Pesticides is their own branch of misery, and PCBs are also a unique compound. And as I've mentioned a number of times, we also have the PFAS emerging contaminants. About 15 years ago, I was working on a manufactured gas plant site, and we needed to figure out what contamination was associated with petroleum, what contamination was associated with the manufactured gas plant tar, and we were going to do some forensic work and asked one of the experts, hey, what are we going to test for? And they said, oh, we're going to do a piano analysis. And I said, what's a piano analysis? And it said, okay, well, we're going to analyze for paraffins, isoparaffins, aromatics, naphthenes, and olefins. And I looked at that list and I recognized aromatics. I didn't know exactly what they were, but after this experience, I said, okay, I need to start work. I never did take organic chemistry in college, so I'm going to start gathering up information on these chemicals to develop at least some understanding, some base level of knowledge. And as I was gathering that information, I put them into a PowerPoint presentation, and that's basically what you're seeing today is my working copy of me trying to keep on top of or bring myself up to speed on organic chemistry. So the first one on the group of chemicals on that list, the paraffins, are also known as alkanes, and that's where how I had heard them referred to as. They're also called straight chain hydrocarbons, propane, butane, octane. So these are single bonded carbon organics, and if you look at this slide, the PFAS compounds are per and polyfluorinated alkane substances. So all you're doing is knocking all the hydrogens off and replacing them with fluorine. When I saw this, I said, is it possible, if you're halogenating octane with fluorine, could you also do that with chlorine? Is there such a thing as chlorinated alkanes? And sure enough, there are chlorinated alkanes. As a group, they're referred to as chlorinated paraffins, more commonly, and they're classified as environmentally persistent, bioaccumulative, they're carcinogens, and they're toxic to aquatic organisms. So if people ask me, what's the potential additional emerging contaminant that we might look at someday, this is high on my list. Okay, the next thing on that piano list was the isoparaffins, and that's branched alkanes. So you start with your alkane, your straight chain hydrocarbon, and then coming off, instead of just a hydrogen, you could have some other organic molecule. And if you just have a CH3, that would be a methyl group, but you can add on longer and longer chains coming off the side of these alkanes. The position that the branch comes off is identified by the number in front of the molecule. So if you see something described as 2-methyl-butane, that would mean you're starting with a butane, and on the second carbon in, you're adding a methyl group. If you have 2,2-dimethylpropane, you're adding a methyl group on each side of that second carbon. Now, so that's a branched alkane, but at the same time you have something known as isomers, and so you can have a molecule of octane that's a long straight chain, or you could actually have a shorter chain with, let's say, a 5-chain alkane with a three more carbons coming off one of the carbons, and that would be an isomer. As long as you've got 8 carbons there, that would still be an octane. So understanding the similarity between branched alkanes and isomers of an alkane is how you get all these different synonyms for one organic molecule, and you can have dozens and dozens of different names for these isomers and branched alkanes, and sometimes the branched chain, sometimes the isoparaffins react very differently than the straight paraffins, and sometimes in some other ways, they act very similarly. So this is definitely a situation where things can get complicated, and you might want to bring in a specialist if you're dealing with this element of organic chemistry. Okay, moving on to the A in piano are the aromatics. The simplest aromatic is benzene, which is just a single one of these rings. All of the aromatics are built on these ringed structures. Most of all the pictures that we see on this slide are polycyclic aromatics, and so they are built of multiple benzene rings, all linked together. Probably the best known of the polycyclic aromatic hydrocarbons, or PHs, is benzoate pyrene. That's the one here in the middle. This family of contaminants are generated anytime you have incomplete combustion of organic materials. Anytime you have a fire involving wood or petroleum or any other organic, if it's an incomplete combustion, you're going to be generating PAHs. PAHs are what make barbecue or grilled food taste good. So they are ubiquitous, but they're also the first chemical that was identified as environmental toxin. The chimney sweeps in London were all developing testicular cancer, and someone noticed that it actually wasn't all of the chimney sweeps. There were some chimney sweeps that were washing their hands before eating, and some that weren't. And it was a matter of one group had recently emigrated to the area, so they had different cultural practices. And that was as soon as they got the people who weren't washing their hands to wash their hands before eating, their rates of testicular cancer came way down. So that was, as I said, the first case of an environmental chemical toxin being identified as a health, impacting people's health. They still did not identify a single one of these PAHs, but it was the soot, and it was recognized that it was the PAHs in the soot that caused that health problem. The N in piano is naphthenes, which are also known as the cycloalkanes, cyclohexane, cyclooctane. These are very common, a common constituent of crude oil, and you'll find it in most petroleum products. The last thing is the olefins, also known as alkanes. Really, the only one of these that you have to know about are the ethene and the family of chemicals that come from ethene, If you start adding chlorine to an ethene molecule, if you add 1, you get vinyl chloride. If you add 2, it's dichloroethene. 3 would make TCE or trichloroethane, and if you put chlorine in each one of those 4 spots, you have PCE, perc, or tetrachloroethylene, which is your typical dry cleaner solvent. All of those are very common organic solvents, and I'll talk more about those later. The one thing I'll mention now is, as you can see, the alkenes or olefins are characterized by this double bond between the 2 carbons. If you add a triple bond, that would be acetylene. So you can have acetylene with a triple bond, ethene or ethylene with a double bond, or ethane with a single bond. If you are, there are a number of ways that you can degrade TCE and PCE. If you're degrading it biologically in anaerobic conditions, you'll move from PCE to TCE, just basically knocking a chlorine off in each case. If you degrade it abiotically, which is what you do if you're using a zero-valent iron, you'll actually move through the acetylene family, and you'll see acetylene as your daughter product of that degradation pathway. So I just wanted to draw your attention to that that pathway and make you aware that acetylene can be one of the things that you monitor for to make sure that your abiotic degradation is taking place. Briefly mention a couple other organic chemicals, but those are the principal organic chemicals that we work with in the remediation field. You do have some alcohols and phenols. Phenol is definitely something we come across on occasion. That's simply this group of chemicals are aromatics with a hydroxyl group added on to it in various ways. There's also ethers. Some of the important or environmentally important ethers include MTBE or methyl terbutyl ether. 1,4-dioxane is an ether as well, and the glycol, propylene glycol, is another thing you might run across. So as we're looking at organic chemicals, we very often have situations where they are forming large groundwater plumes. And the propensity for any one of these chemicals to create a groundwater plume is described in this equation here, where you have the fractional organic content and the partitioning coefficient. So in general, the more all of these organic chemicals bond very nicely to organic carbon. That's one of the very nice things about these chemicals. If you have them in your drinking water supply, the granular activated carbon filters are generally very effective at taking all of these out. The exception to that rule is 1,4-dioxane, where that is so hydrophilic. It loves staying in the water. It's very, very difficult to remove 1,4-dioxane. But almost all of the other organic compounds are removed very nicely with the organic carbon. So the more organic carbon, the less groundwater contamination you'll have for a certain amount of these organic chemicals. And then each one of these organic chemicals has a particular partitioning coefficient, its tendency to dissolve into the water. And those are numbers that you can look up in any number of references. One other interesting thing about the standards for protection of groundwater, so most states have a soil cleanup standard set for protection of groundwater, and they tend to be significantly higher than a straight calculation of fraction of organic content times the partitioning coefficient, because you do get some dilution or attenuation of these chemicals. All these chemicals will degrade over time, and if you have a small source of this chemical, it will go down with rainwater and mix with a larger volume of material, of groundwater that's already present. And that is captured by this factor called the dilution attenuation factor, or DAF. New York, when we were developing our soil cleanup objectives, used a dilution attenuation factor of 100. And that seemed to work pretty well. As we're looking at developing a protection groundwater number for the perfluorinated compounds, it's becoming increasingly clear that that number of 100 is not going to be appropriate for use in this situation for two reasons. One is that those chemicals do not degrade in the environment. They are remarkably persistent, and they don't degrade from either chemical actions or biological activity. The other thing is, as I was mentioning, the two elements of the dilution attenuation factor is the attenuation and then the dilution. So if you have a small area, discrete source of PFAS contamination, you actually might get some significant dilution taking place. But if you were to have a large area of air deposition, for instance, where you have square miles of relatively low-level soil contamination from an air discharge, you wouldn't have any dilution to speak of either. So you would your protection groundwater number would be much lower. It would be the unaltered FOC times KOC value, or if everything is working well, that would actually be your SPLT result if you're doing that analysis. So you could, if you have a large area, you could end up with the SPLT result describing the relationship between soil contamination and groundwater contamination. Okay, deep breath. That was our basic general organic chemistry review, and now we'll start talking about sources of these organic chemicals. Probably the most common source of organic chemicals is petroleum. There is obviously the petrochemical industry is huge. Gasoline is probably the most common. Gasoline will have more volatile components than the other petroleum products. Diesel and kerosene, much lower volatile content. Surprisingly, at least to me, jet fuel is very similar to diesel and kerosene. You can actually also find some number 6 fuel oil, which is very viscous. It actually has to be heated in order to flow. Very little volatile content. It's also known as bunker fuel. If you have a spill of number 6 fuel oil, it's almost impossible to pump out of the ground. That's the downside. On the good side is it doesn't flow very well either, and we certainly have deposits of number 6 fuel oil underneath buildings where it was used as a heating fuel, where we know there's a spill there and it just isn't going anywhere, and we're just monitoring that situation. So number 6 fuel oil is a unique material. So as the crude oil comes out of the ground, there's a fairly wide range of distribution of these component chemicals. The paraffins can make up anywhere from 15 to 60% of the crude oil. Naphthenes may be anywhere from 30 to 60%. Aromatics, 3 to 30%. That's a tenfold difference between that range, within that range. And that's the asphaltics, the things that you would use for the number 6 fuel oil or the road asphalt, probably no more than 6%. That range of composition in the crude oil is not really the same range that we use the crude oil. So we have probably the highest demand for crude oil is gasoline. If the crude oil only has 6% naturally of gasoline range organics, we have to somehow make up the rest of that in the refining process. And usually the way they make up that difference is by cracking the larger molecules into smaller molecules. And the exact processes that the different refineries use to change the makeup of the crude oil to address the difference in supply and demand of the specific compounds can actually make up a fingerprint. So someone doing a forensic analysis of petroleum can tell what refineries the petroleum product came from based on those processes that they used. One other thing that we have to mention when we talk about petroleum is tetraethyl lead. It was invented in 1921 to improve performance, to eliminate the knock that was prevalent in internal combustion engines. It was invented by Thomas Midgley, who later came up with Freon. So between the two of those, someone came up with the quote that he possessed an instinct for the regrettable that was almost uncanny. There's a great article that was done, I believe, by The Atlantic called The Secret History of Lead. And even back in 1921, when they were trying to address the anti-knock issue, ethanol was seen as an equally effective product, but the people who were making the tetraethyl lead were able to wage a marketing campaign to get that used instead of ethanol. And it's that simple a thing that led to the large amount of lead that was released into the environment from leaded gasoline. And there were large numbers of deaths and lead in the factories creating the tetraethyl lead. So tetraethyl lead is certainly one of those unfortunate stories of the industrial age. And so one of the acronyms you'll hear commonly regarding petroleum contamination is BTEX. BTEX stands for benzene, it's an acronym for benzene, toluene, ethylbenzene, and xylene. These are the four most common aromatics in gasoline. Fortunately, they degrade aerobically. They degrade very readily. You don't need a very specific bacteria to break it down. So in general, we don't see long plumes of BTEX coming from leaking underground storage tanks. If you have anaerobic conditions, you can have a more significant groundwater plume associated with that, with a spill. Or if you have pure product, the pure product doesn't break down nearly as well as the dissolved product. The BTEX compounds are volatile. We don't see a lot of issues with, or as much of a concern with vapor intrusion from petroleum because the vapors also degrade aerobically. So in general, unless you have really gross contamination very near a building, or unless you have a preferential pathway, the degradation of the BTEX compounds in the vadose zone will adequately address that concern. But you can, because they are highly volatile, you can have petroleum vapor intrusion in special circumstances. These, certainly are toxic chemicals, particularly benzene. That's one of the earlier, better studied toxicological profiles. So that's just touching on petroleum. Now I want to talk about coal tar, which is the other really significant another significant source of organic chemicals. Early on, the manufactured gas plants were all using the coal carbonization process. Interestingly enough, this process was originally developed to make the tar. So the tar was used for waterproofing, especially in the shipping industry, and the plants that they were using to make the tar kept blowing up. So they found that there was combustible gas that was coming off of the coal as they were making the tar, and that became a valuable byproduct. And fairly quickly, the tar became a secondary material, and the primary material became the combustible gas or the coke that was also produced. So once you've taken all the volatiles out of the coal, it became coke, and that was critical for the steel industry. And then the combustible gas was used to usher in the gaslight era. And it was big news when your municipality got a gas plant, because you went from candles to gas lights that you could turn on the wall, and you went from a wood stove or coal stove to a gas stove that worked just like the stove you have in your house now. While coal carbonization was the principal process used to make that combustible gas, the tar was generally a highly valuable byproduct, and it was managed fairly well. Unfortunately, they developed a process called the water gas process, which created a higher BTU gas for distribution, and it used petroleum as the feedstock. Unfortunately, the water gas process created a much less valuable tar. It formed an emulsion with water, so it was very difficult to handle. It had a lower viscosity, so once it got out into the environment, it moved through the ground more easily. Interestingly, depending on how the plant was operated, the tar from a water gas plant could have very different properties. If the plant was running a little bit cold, the tar would basically be a condensate from the feedstock, so you'd have basically recondensed petroleum in your tar. If you ran it hot, it would be much more concentrated in the polycyclic aromatic hydrocarbons, those bigger molecules, and it would be much closer to a coal carbonization tar. And most plants had tar handling equipment to manage this, especially if the plant was a water gas plant from the beginning. Some plants didn't have any tar handling equipment at all, and if that was the situation, you could have a huge contamination issue from a relatively small plant. These plants were notorious for odors and bad housekeeping and so on, And when they referred to the early 1900 St. Louis Cardinals, I believe they were, as the gas house gang, that was not a compliment. Because the folks who lived near the gas houses tended to be the rough and tumble sort. So here's another picture of MGP tar. Very often when they decommissioned these sites, they dumped all of the buildings into the holders, and the holders tend to be filled with tar, so you have a lot of rubble mixed with tar when you're doing your excavation. As you move away from the source areas, what you see is the tar moving through the ground in seams. This was a relatively small seam, and you can see the tar filling the test pit over time. I mentioned early on trying to differentiate between coal tar and petroleum. Very often you have sources of both chemicals at a site. Rather than going through some elaborate process, very often all you have to do, especially if you have source material, is to look at the chromatogram. A chromatogram of coal carbonization tar will be a series of very specific spikes, as you see in the top right corner, whereas petroleum will have a hump of undifferentiated, really complex materials that the chromatograph really can't differentiate sufficiently. So just by looking, you can see the difference in the chromatogram between the tar and petroleum. Okay, I want to talk a little bit about chlorinated solvents, because these are a very, very important contaminant that we all deal with. It does have a specific gravity greater than 1, so it acts as a denapple, as pure product, which means it drops through the groundwater until it comes to a lower permeability material, like a clay. And if that's a continuous layer of clay, it can pool there and be an ongoing source of contamination for indefinitely, basically. It does have a low vapor pressure and a Henry's law constant, which leads to really significant soil vapor intrusion, both in the beta, from soil contamination in the beta zone, and from the contaminants coming, volatilizing off of contaminated groundwater. One of the things that made these very effective solvents is their ability to penetrate into small fractures, like engines and so on. So if you were trying to clean out a dirty engine, these solvents would remove the dirt and the grease very efficiently. That penetrating ability also gets these solvents into bedrock, into clay, and once it gets into those materials, it's very, very hard to get out. So that's one of the physical properties of these solvents that makes remediation challenging. These chemicals also do not degrade aerobically. We weren't aware of any way that these degraded biologically until I believe it was a military base on Cape Cod, where they were chasing a plume of TCE, and it went underneath the landfill, and when they went to look at it on the other side of the landfill, it was gone. And there was some part of it passing by the landfill to the side, but clearly something was going on under the landfill that was degrading that TCE plume. And when they went and investigated it further, they identified that the Halosecoides bacteria, which is still the most widely known of the Halobacter bacteria that will degrade these chemicals. I just mention as a side note that trichloroethane, 111 TCA, is an ozone depleting substance. So if you're selecting a remedy for a TCA site, think twice before selecting soil vapor extraction. And if you are selecting soil vapor extraction, definitely seriously consider treating that with vapor phase activated carbon so that you're not putting more ozone depleting substances into the air than necessary. Okay, as I've mentioned a couple times, the soil vapor intrusion from these organic solvents is a very significant problem that we're dealing with now. It really wasn't considered a problem until 2002 when EPA lost a lawsuit out in Colorado, and after that they were the edict went out that first for reckless sites and then for surplus sites as well, this pathway had to be evaluated. Let's see. That first round of guidance that EPA produced for vapor intrusion assumed that all the vapors were coming from contaminated groundwater. That's probably because that was the way things were working in that first case in Colorado. The more we've seen vapor intrusion sites, the more important the remaining residual contamination in the Vados zone is for vapor intrusion. If you have a release of contaminants from a building, from a dry well inside a building, for instance, the area underneath the building isn't flushed by rainwater, so you tend to have a higher concentration of the organic solvents in the Vados zone above the groundwater, and those will act as a continuing source for the solvents getting into the building, and it's definitely something to be aware of for vapor intrusion sites. Okay, I've mentioned reductive dechlorination a couple times. This is just a visual for that, where, as you see, the picture on the left shows trichloroethane, and you have 3 chlorines and 1 hydrogen. If you knock off another hydrogen, you'll have dichloroethane. Knock off another chlorine and leaving 3 hydrogens, 1 chlorine, that's vinyl chloride. The reason I included this slide is because if you knock off that last chlorine, you're left with ethene. And early on, we weren't monitoring the ethene production, and we assumed that if you weren't seeing a significant amount of vinyl chloride, you weren't getting full reductive dechlorination. But in the last 5 years or so, people have increasingly been looking at ethene as to evaluate the effectiveness of reductive dechlorination, and we've definitely learned something from that analysis. There are times when you don't see any vinyl chloride, but you see a lot of ethene, and based on that, you recognize that the reason you don't see the vinyl chloride is it just is degrading faster than the DCE is degrading. So you can have situations where you're getting full reductive dechlorination even without seeing a lot of vinyl chloride in the environment. The other thing that was learned from monitoring for ethene is if you look at the source areas, the original assumption was that the source areas were too toxic, too concentrated for the bacteria to get in there and thrive. But when they started monitoring for ethene production in the source areas, they found huge productions of ethene. So there doesn't appear to be that limit for the bacteria. They can survive in very high concentrations of these chemicals, and the reductive dechlorination is taking place right in the source area. We just weren't seeing a measurable reduction because there was so much of the chemical in those source areas. If you are using reductive dechlorination as an element of your cleanup, you're going to want to monitor some of the attenuation parameters, some of the characteristics that keep that process working. You don't want to have dissolved oxygen in the ground. You want to keep that below half a part per million in order to keep your dehalogenating bugs happy. You also want to have oxidation reduction potential, which is highly negative, ideally in the minus 200 to minus 300 range. One of the other very common ways that we treat these organic solvents in situ is with in situ chemical oxidation. Just wanted to point out what the final products of that reaction are, which is generally oxalic acid and chlorine. So you will have a chloride plume coming off of an effective in situ chemical oxidation project, and that's one of the things that you can measure to demonstrate effectiveness. Taking a quick look at a couple other remedial technologies for the chlorinated solvents. I mentioned soil vapor extraction. If you have that beta zone source where you have highly concentrated vapors above the water table, you can have a blower pull those vapors out of the ground, and you can also add sparge points where you're adding air into the below the water table to bubble the vapors out of the contaminated water, and that would be an air sparge soil vapor extraction system or an ASSVE system. Definitely very effective, and the SVE systems are almost what's the term? Presumptive remedy if you have an active building with significant amounts of beta zone contamination underneath, and very effective. You don't have to pinpoint the contamination to get it out. With all these tricks or tools that we use for organic solvents, whether it's in situ chemical oxidation or reductive dechlorination or soil vapor extraction, they work very well in high permeability soils. They work really poorly in low permeability soils. So understanding your geology, creating that good, accurate conceptual site model based on the geology of the site is absolutely critical if you want to do any in situ remedy for the chlorinated solvents. This is just an illustration of that. As the organic solvent is released into the environment, it moves down through the water table until it finds a less permeable material of aquitard, clay, or bedrock, and then it penetrates into that clay or bedrock, and that becomes your long-term source. One of the descriptive terms they use is diffusion-limited conditions, where the rate at which it back diffuses out of the low permeability material will dictate the concentrations in the environment. Most treatments can't penetrate that clay. You can still excavate. That always works. You can get chemical oxidant in contact with that contamination if you mix the soil, and the in situ thermal remedies will be effective too. The thermal remedies are expensive. They're also they're disruptive to the site, you have to put heating wells in a fairly tight spacing, but they absolutely do work. And if you need to have the site cleaned up quickly with a guaranteed result, the thermal remedies certainly have carved out a niche for themselves. Okay, I'm going to just run through a couple last two things, PCBs and the PFAS compounds. PCBs are unique. They're these two rings joined by a single bond. The PCB mixtures were marketed by Monsanto as aerochlors. There wasn't an exact composition. They were shooting for a target percent chlorine by weight. So aerochlors typically had a number 12 to begin, and then the second two numbers gave the percentage of chlorine by weight. So aerochlor 1221 was 21% chlorine by weight. 1242 was 42% chlorine by weight. The higher percentage chlorine, the more toxic it was. You're definitely, when you see the 1254 and the 1260 out in the environment, something to be aware of. As I said, the aerochlors, they were shooting for a percentage chlorine by weight, but you had a wide range of individual congeners. So exactly which of the 10 locations on those molecules that could potentially have chlorines on them, it was a mix. So if you're trying to differentiate between aerochlor 1242 and 1248, a degraded aerochlor 1248 might look an awful lot like an aerochlor 1242. So differentiating between aerochlors can be more of an art than a science. The more specific evaluation for PCBs is the congeners. There are 209 different ways that you can mix and match the chlorines on those two rings, and each one of those different combinations given a BZ number or IUPAC number. So that's the other way you can look at different PCBs. But in general, from a regulatory standpoint, EPA, TSCA, and most states do look at PCBs as total PCBs and don't make a differentiation between the different aerochlors, the different congeners. There are states that regulate PCBs as aerochlors, so that's not a consistent statement across different states. There are some congeners that are more toxic than others, specifically a group of dioxin-like congeners that the World Health Organization has identified as really highly toxic. World Health Organization has suggested some much lower limits for those chemicals. To date, EPA hasn't followed suit, but that's something to be aware of. Similarly, another branch of PCBs, the hydrolyzed PCBs, may be more toxic than the PCBs that we're looking at right now. These would be PCBs that have undergone some biological reaction to become hydrolyzed in place. The health concerns associated with PCBs are typically based on the effects that the PCBs, which have become hydrolyzed inside the receptor organisms, are having. So there's current research to look at whether there's significant concentrations of the hydrolyzed PCBs out in the environment. PCBs were very useful chemicals. They were used for fire retardants, insulators, capacitors, dielectric fluids, caulks, paints, sealants. That's why there's so much PCB out. There are so many PCBs out there in the environment, and why we should probably screen sites for PCBs even if we don't suspect that they were used at a facility. You never know where they turn up. You'll find PCBs at electrical substations, wire coating facilities, paper plants that use NCR paper, capacitors, et cetera, et cetera. So, one other thing I'll mention about PCBs is they are regulated by TSCA, which is not a delegated program. So EPA will have something to say about any CERCLA cleanup involving PCBs. I'm going to go through PFAS compounds fairly quickly because I'm sure there will be other follow-up discussions on these chemicals. Per and polyfluorinated alkane substances, PFAS. There are hundreds, probably more accurately thousands of different compounds that have these either fully fluorinated or partially fluorinated alkanes. In the early 2000s, the Washington Works plant in Parkersburg, West Virginia, was identified as a significant Superfund site. Result of that was one of the results of that cleanup was a very substantial health study. So this is one of the more heavily studied chemical families in recent years. They did find some significant concerns during that health study. Soon thereafter, they included the 6 of these perfluorinated chemicals in the unregulated contaminant monitoring rule, monitoring for drinking water supplies, and that did identify fairly widespread presence of these chemicals in water supplies throughout the country. And that's how we find ourselves in the current situation. The perfluorinated compounds, the ones that are fully saturated with fluorine, are remarkably stable and persistent. The sulfonates, PFOS as opposed to PFOA, are fairly highly bioaccumulative. The other acids, not so much, but the sulfonates certainly are bioaccumulative. The health concerns start at a very low level. They run lots of lab studies on lab animals, got high toxicity levels and strong responses to the doses. The levels of concern came down even further because these chemicals have a much longer half-life in humans than they do in the lab animals, so that's a multiplier. So it's, we certainly are seeing health concerns at concentrations much lower than other chemicals. The polyfluorinated alkanes, the ones that aren't fully saturated, they will break down, and as a result, you can end up with different compositions in your groundwater plume down gradient as the polyfluorinated alkanes break down into smaller perfluorinated compounds. We have seen sites, you can do a test called the total oxidizable precursor assay, where they take a sample, oxidize the heck out of it, and then retest it again. And we've had such tests where in the first test before oxidation, we only had a couple parts per trillion of PFOA. After the oxidation, we had over 20 parts per trillion of the PFOA and PFOS. So we saw that there are states where that would be above the standard. So we definitely have seen situations where you can have an order of magnitude increase from the precursors. When we're evaluating the PFAS compounds in New York State, we're evaluating a list of 21. This is certain to increase in number over the years as more compounds are identified and become commercially, standards for these compounds can become commercially available for the labs. The uses of these chemicals, coating fabrics and tapes, the Superdome, Denver Airport, those were all built with treated fabrics from the Northeast. The perfluorooctanoic sulfonate is a key ingredient in Scotchgard and other stain repellents. Also used in aqueous film forming foam or firefighting foam, which is used anytime that you're fighting a fire with gasoline or some other fuel that could be a concern. So any airports or fire training centers where firefighting foam was used in training activities or where there were major accidents, you could have the PFOS and other related chemicals showing up in your groundwater. And this wouldn't intend for you to read this entire slide. The intent is to show you that these chemicals are used in a wide range of industrial activities. So we are still learning about all the different ways that these chemicals are getting into the environment. And with that, thank you very much, and I'll turn it back to Jennifer.
Great, thank you, Bill. And this is his contact information if you have any questions about all the great information that he presented on the webinar and this recording. So with that, I think we are all set. I'm going to with this recording. Thank you.